Okay, there we go. Got it. Right, okay. Hopefully you can all see my screen. My name is Max Richards. I am an energy transition consultant at OPC. I have a master's thesis in carbon capture and storage. Today we've got a really interesting presentation for you. We've got a series of presentations. The London SPE Net Zero Gaia Committee, with thanks to our sponsors OPC and ERC Evolution, is very excited to bring you a first of its kind lunch and learn for the SPE Gaia Committee. We're going to have two carbon capture and storage industry experts giving technical presentations covering flow assurance and reservoir engineering, hopefully drawing from example projects. When we were putting together this schedule for the event, we sat down and thought, what can we give you the most relevance, and drawing from some of the stuff that we've done at OPC with our clients, flow assurance and reservoir engineering is what we thought was important. There are key technical barriers that need to be constrained and understood for developing CCS globally. Flow assurance, including the modelling of CO2 and impurities from surface facilities through to pipelines and wells, ultimately for injection, is highly complex, requiring advanced modelling techniques. Reservoir engineering, from depleted gas fields to maturing carbon storage projects from theoretical to practical storage, includes technical management, objectivity modelling, near wellbore management, and plume development. So to help us understand these critical technical challenges, we will be joined by experts from OPC and PACE CCS, each of whom will present their topics and answer audience questions. So I'll tell you about the format of today's presentations, but first I'll just introduce our two hosts or two presenters. So the first one is Dr. Eduardo Luna-Ortiz, who is the Technical Director at PACE Carbon Capture and Storage. Dr. Eduardo is the Technical Director. It's a PACE CCS, a consultancy based in London. Eduardo holds a BSc in Chemical Engineering and a PhD in Chemical Engineering from the University of Manchester. He later joined Imperial College London as a postdoctoral research associate, where he pursued the development of multiple phase flow modelling, computational CO2 thermodynamics, advanced control of fuel gels, green hydrogen production, and numerical methods. Eduardo has worked in a number of consultancies that many of us know, including Exodus, Genesis, and FISA, now known as KBC Advanced Technologies. Over the past 16 years, his involvement in the energy transition sectors includes carbon capture storage, projects such as HyNet, VNet Zero, Porthos, Mumba, and H2, production, transport, and storage. And our second presenter today is Anzhela Lodge, who's a staff reservoir engineer at OPC. Anzhela works here in London with myself. She holds a master's in petroleum engineering from the Imperial College London and formerly worked for Schlumberger. Anzhela has gained significant experience in all reservoir engineering, both in the North Sea and internationally, having worked for both OPC and multiple operators. Anzhela has significant experience with dynamic modelling, reservoir management strategy, field development, and well performance monitoring through PTA. Her skills include reservoir simulation projects using Eclipse, T-Navigator, production forecasting using PETEX Suite, and pressure transient analysis using Pi and Sapphire. More recently, Anzhela has worked on several CCS projects at OPC, from prospect injectivity modelling all the way to full field dynamic simulation of CO2 injection. Some of the projects that I've worked on Anzhela with. So that's who we're going to be speaking to today, or hearing from. In terms of the format, so we've just got a 5-minute introduction that I've done. Eduardo's got 20 minutes to give his presentation. Angela's going to then have 20 minutes, and then we'll have questions and discussions at the end. If you have any questions throughout the presentation, please put them in the chat and we'll address them at the end. And of course, a simple reminder that it will be recorded. I think that's everything from me, unless Barney, I don't think I've missed anything. So I will hand over to Eduardo.
Thank you for the introduction, Max. I hope you can see my screen. If somebody can confirm.
Yeah, full screen, and yeah, it's perfect. There you go. That's everything. Thank you.
Thank you, Max, again for the presentation. So I'm Eduardo Luna from PACCS, and I'm very happy to be here this afternoon to talk about flow assurance and CCS systems in general. And well, probably you know that we need to decarbonize an industry, and we can do it for many ways, not only CCS. So we can do energy process efficiency, minimization of energy consumption. We can change fuels. But it's a fact that we need to reduce emissions mainly from the industry. However, decarbonization means different things for different people. How do we measure decarbonization? For example, we can measure it with CO2 release versus the resource uses, the temperature increase of the planet. We can measure it in the effects of climate, climate change, the availability of resources, the uses of and needs of products. We can also measure it with the 17 Sustainable Developments of the United Nations goals. And how do we measure? How do we decarbonize? So one way is to reduce CO2 emission by reducing energy demand. One way, which is part of the talk of this afternoon, is to utilize the captured CO2 or generate only the amount of CO2 that can be captured and utilized, and that's process efficiency. We can look for integrated solutions taking into account regional constraints. How can we do it? Or what are the means to decarbonize? We can integrate ideas or new concepts to develop significantly better technologies. We can use new conversion and separation technologies. We can develop and use computational methods and tools that give significantly better solutions. And perhaps a bit more controversial, we can change the business paradigm from maximizing, instead of maximizing profits, to maximize sustainability, including social and ethical constraints. And when we talk about energy transition, one of the questions is why we not only change to renewables, or why we not only use renewables. And well, the current deployment rates is not enough without significant deindustrialization, and it will require a lot of investment and perhaps even political willingness. In reality, we will still depend on hydrocarbons, but as I said, we have to make sure that we minimize the emissions of those hydrocarbons. Moreover, renewables cannot prevent emissions of hard-to-abate industries like steel or cement. CCS is probably going to be one of the pillars in the energy transition. It's not the silver bullet, so it's not the, as I said, it's not the only thing that we can do. But by doing this, we have to make sure that we not prevent the increasing efforts through green energy. I want to speak about CCS, but before that, I want to speak a bit about other type of opportunities to decarbonize or to reduce CO2 emissions. And one is energy efficiency in operations. For example, we know that distillation columns are very energy intensive, and that means emissions. The long-term solution will be a total replacement of these columns. The question is if there are membranes or related materials to totally replace these industrial columns, and the answer is we're not quite yet. The short-term solution is to use a hybrid scheme, an integrated scheme. So integrate existing columns with small membrane operations, and that will reduce consumption. However, this needs optimal design to combine both unit operations so that each operation or each unit operates at the highest efficiency. And by doing this, we can maybe save between 10 to 50% of energy savings, and therefore we reduce the emissions. And this actually is a lot of opportunity. We can actually minimize a lot of CO2 or a lot of emissions because, for example, just for distillation columns, there are about 200,000 operating distillation columns. So that will be quite a lot of energy savings. No? And by doing these little savings on efficiency, before we start talking about CCS, I think with potential we can get to the to minimize those emissions. But now I'm going to talk about CCS, which is the topic of this Launch and Learn. We are going to be talking about the industrial CCS cluster. So we have a number of emitters, which will be an industrial source like a fertilizer or cement plant. We're going to have maybe power. We're going to have biomass or direct air capture or blue hydrogen. And all these industries, we're going to capture the CO2 and we're going to be putting into a gathering network. And then we're going to transport this CO2 into perhaps offshore CO2 storage, and that's going to be permanent. This is not EOR, that's a different story. We're going to be just talking about permanent CO2, so that CO2 is not being used to produce more oil. We can also perhaps ship that CO2 to other clusters, for example. So this is what we know as an industrial CCS cluster. But this brings challenges, because we're going to have multiple users, and by that I mean different industries, current industries, as I said, but maybe in the future, new users are going to tie into the network. And these users are going to be very different. They're going to be different sizes. We're going to have very big emitters or with the small emitters, different industries, as I said, from cement, power, steel. And each one may use a different capture technology with different solvents or different dehydration technology, etc. The fluid, the CO2, is going to have transitions, perhaps, and by that I mean it's going to transition from gas to liquid or supercritical, and that could happen, well, in the reservoir, perhaps, and I'm sure Anzhela is going to talk about it, maybe. But for sure, it might happen also in the network, and there's something that we need to manage somehow. More importantly, well, perhaps not important, but also very important, is that the CO2 is never going to be pure, and we're going to have a lot of impurities. And that is very important. So, and that's when the PVT or the thermodynamics is important. You need to know your fluid, because, as I say, it's not going to be 100% CO2. It's going to be a lot of stuff, like the numbers or like the species that I'm putting here. We're going to have gases or light gases like hydrogen, nitrogen, argon, CO2, which are mainly from combustion of fuels. We're going to have maybe lighter hydrocarbons. We're going to have water. We're going to have oxygen, NOx, SOx, and other stuff. No, and we're going to have inclusive solid particles, glycols, nitrosamines or nitramines, which are the degradation products of the amines. So the potential species that we're going to have in the fluid that is going to be transported eventually, also going to be stored, is quite huge. It's very diverse. So you need to know what is being transported, and you have to assess whether the storage is going to be able to accept this, and also the pattern, of course. The impurities, from a thermodynamic point of view, it causes a lot of challenges, or a lot of issues. For example, different amount of water may have different dew point. For example, 50 ppm of water, you're going to have a dew point of -30. You're going to have 2,000 ppm of water, your dew point is going to increase to, I don't know, 35 centigrades. The impurities also may cause different corrosion rates if there is water. So as you can see in the figure in the right, top right, depending on the impurities that you have, or the mixture of impurities, you will have different corrosion rates. So it's important that if you're going to allow corrosion, which is something that you shouldn't allow, but if that happens, these corrosion rates are going to change quite significantly depending of the impurities. MEG and TEG, glycols and amines, also they caused a very strange particular behavior. Here I have two different compositions. They will induce some liquid dropout or liquid droplets, and they will induce quite what we call an exotic thermodynamic behavior. And that is just because you have different impurities. So you need to make sure that you predict this type of behavior. You have species like hydrogen, nitrogen, or argon, which may induce the enlargement of the two-phase flow, and then something that we don't want to flow. So that is going to increase your operating pressures if you want to flow in liquid phase or dense phase. So you have to make sure that you be able to predict more or less accurate this the bubble point and the dew point. So the point is that the impurities, even the small amount of impurities, is going to have an impact. So assuming CO2, pure CO2 is not necessarily the best practice. But also, with the amount of impurities or the different impurities, we may even have chemical reactions, and not only chemical reactions that may cause, for example, production of sulfuric acid, which that's not a good thing to have in the pipeline. But we may also have stuff, for example, CO2 and ammonia, and that's going to produce salts, ammonium salts. And that we don't know if actually, well, we think that obviously it's not a good thing to have salts in the pipeline, because might accumulate, I don't know, in valves or things like that, or if they have in transport, they might also get into the pores of the reservoir, and it might reduce injectivity. So the fluid, as you can see, I hope you can see that it's very complex, and you may have a lot of different phenomena occurring. So it's very important that we start investigating this type of behavior of interactions that happens between the CO2 and impurities, and between the impurities themselves. One of the questions that is being asked very often is, what is the best equation state for the thermodynamics? And the truth of the matter is that there is none. And actually, it depends on the chemical nature of the compounds. Also, it depends on how the model and the results are going to be used. And of course, also very important is where it's implemented. No, if you're gonna write your own software, maybe okay, fine, you can use a particular equation state that you like. But if you're gonna use, I don't know, HYSYS or Aspen that has a particular set of equation states, then you have to make sure that whatever you use is good. No, I'm part of a working group of the Energy Institute. And we will gonna issue a report probably well, I think it's gonna be more like October this year. And this report is gonna review equation states and the experimental data available for CCS fluids. And basically, the main conclusion is that there's not a single equation state that for CCS fluids. No, so it depends on what you use. No, and I like this. This slide because after several, we have equation state for more than 3 centuries, and we still don't have a universal single thermodynamic model that is used or it can be used for any application. And I think I just wanted to kind of emphasize the fact that we cannot keep asking what is the best model. No, I think you just need to kind of investigate what is your application, and then based on your application, then you can select the correct or the best equation state for that particular application within the CCS fluid. However, any model that we want to use is going to have limitations. For example, might fail near to the critical region, might not have very good liquid density predictions. It might be very expensive or maybe very computationally expensive. You cannot use it, for example, for reservoir simulation. Maybe, as I said, maybe it's not compatible with whatever simulator you're going to be using, etc. However, all the models should be tuned with experimental data. However, as you may know, data, at least for multi-component mixtures, for example, like the one that I showed a few slides earlier, is non-existent. And even binary mixtures, for example, CO2 and, I don't know, hydrogen, or CO2 with other components, is also very scarce. But however, there is some information, and if you have the information, just try to kind of tune your equation state to that experimental data, because it really, as shown in this figure, it really kind of improves your thermodynamic calculations. Also, the other important thing is the consistency of the equation state through the different, through the whole chain of the CCS system. Because what we don't want is that you have a plant or a capture, a user that captures and compresses X amount of CO2, and then the pipeline transports a different amount, and the reservoir stores a completely different amount. So it's very important that we keep the same consistency through the thermodynamic consistency through the different parts of the CCS system. So sometimes we segregate the subsurface, and the surface we kind of don't communicate, as probably also happens in conventional hydrocarbons. But particularly in CCS or CO2 transport or CCS networks is more critical, because this really leads to big discrepancies. And these discrepancies is mainly because we have the CO2 properties, or the properties of the CO2, particularly when we operate very close to the critical region. They change quite significantly with small changes of temperature and pressure. So if we don't have a consistent or integrated model through the for the network, we're going to have quite a lot of discrepancies, and you can have a look at that paper of some guys from Petronas, which they describe one study case, and it's very interesting. And one of the options that we can do integrated modeling to ensure thermodynamic consistency, well, there are various. One way is to use something that is called Cape Open. Cape Open is I want to call it some sort of software communication. So basically it allows using a thermodynamic model to be used in a sort of plug and play in various simulators. For example, a thermodynamic model that is developed in Multiflash. Multiflash is a thermodynamic package. It can be used in process, in HYSYS, using the same Multiflash models. So in a way, it would call Multiflash, if you want to put it like that. And that will make sure that you always use the same consistent thermodynamic model. This Cape Open socket, it allows the thermodynamic model to be used in plug and play in various process simulators. The problem is that not all the simulation tools are Cape Open compliant. For example, if you do flash runs, Olga is not Cape Open. Another option is to use a software called Maximus, which is an integrated production modeling. Is for the people that do flow assurance and process facilities, is something that we use to do life of field simulation for oil and gas systems, of course. This is a third-party simulator, and it can be used with Multiflash, which is from KBC. It's a good simulator. It's a good idea because it connects also with Petrosim, which Petrosim is the process simulator of KBC. The good thing is that using this combined or integrated model, we have rigorous pile and well thermohydraulics, and of course consistent thermodynamics. If you have a subsurface, the reservoir model can be used. It uses a simplified model, a tank model, and as I said, it's very useful because you can have a life of field simulation. So you can simulate, I don't know, 30, 20 years of the project cycle, no? But it's a steady state simulator. A third option, and this is something that we do in PACE, is we have a digital, we call it digital CCS simulator. And we want to understand how quickly a CCS network will operate across the project cycle. And we have, as I showed at the beginning, we could have multiple emitters connected to the transport network. And we can store, or we can, and also it can be connected to multiple wells and reservoirs. Because we have multiple reservoirs and emitters, the conditions change over the field life. The reservoir pressure increases as you store more CO2. The flow rate changes, as I said at the beginning. We have different emitters tying into the network, and everybody's going to have different flow rates. Everyone is going to have probably different composition, but within the same overall specification. And we can also see them have phase development, so you can have compressors, stage compressors at different points in time. Also, it's important that we have this type of models because there is limited operational experience, or actually there's no operational experience because there's no an industrial CCS with so many meters connected into the same network. And we developed this as a custom-made web-based software. And it uses a thermodynamic model of choice, and we can use it via lookup tables, or perhaps we use a machine learning of some surrogate model. It can also allow us, which is something that the other two approaches, it doesn't, but you can also use some sort of transient thermodynamic model for single phase elements. And when I mean transient, it's not necessarily years. I'm talking about short-term scenarios like, I don't know, shutdown or a startup, things like that. We can also have a simplified model of the reservoir. There is a surrogate model or a tank model for the storage. And we have used this for one of the projects, for example. And here we were investigating like how do this well, it's a system which is in this case just one source, so one emitter, and we wanted to investigate how the flow splits to 3 different reservoirs, and these 3 different reservoirs they have at a specific point in time they have different reservoir pressure, and we wanted to investigate like how does the flow split or how the flow splits in an uncontrolled offshore manifold. So that's just a natural split just by hydraulics. And this includes just, integrating the flow assurance, so the thermal hydraulic and the thermodynamic model and well and reservoir models. And we cannot build this without any third-party software. The well and the reservoir model uses a surrogate model to match organic results. And this will give us good results now. Unfortunately, I can only speak of what it is because I'm not allowed to show the results of this one. Anyway, so finally, I think concluding remarks is for CCS projects, I think we can see that integrating surface or subsurface approach is very important and is even more crucial in CCS projects. The thermodynamic model, I think, remains a challenge. And one of the key challenges is to keep consistency across the whole chain. And there are various options to integrate subsurface and subsurface with consistent thermodynamics. And this is my last slide, Max. Thank you.
Thank you very much, Eduardo, for the presentation. Just a quick note for everyone. We'll do questions at the end. But yeah, Eduardo, I think we need to sit down and have a chat because we do a lot of reservoir modeling side, and we've done some investigations into what effect the impurities will have on injectivity modeling and plume development. And you can see there's a significant difference, and that can be increasingly important for your well design or perhaps your limitations of your acreage. Yeah, it's hugely important. And thank you very much for your presentation. Really appreciate it, giving us your time today. So I'll invite now Anzhela to share your screen and give the presentation. Thank you, Anzhela. So yeah, a quick introduction again. Anzhela is Reservoir Engineer at OPC, works with me. And yeah, over to you, Anzhela. I can't hear you or see you.
Oh, yes. Sorry for that. There
we go.
I think you can see me now.
Yeah, I can see you. I can hear you. Right, over to you.
Perfect. Thank you very much. Hi, my name is Anzhela, and I'm Reservoir Engineer at OPC. So I'll start with a short introduction to OPC, who we are and what do we do. Oilfield Production Consultants is a global upstream technical services consultancy. The company is about 35 years old and was established in 1987. We specialize in subsurface production engineering and geosciences, with the project varying from quite specialized to the full field development planning, CPRs, reserves audit, etc. There are 2 sides to OPC, which is consultancy services and internal technical team, and from consulting services as well. They can provide they can provide individuals specializing in particular areas to the full teams, which we've done in the past. We have 8 offices across the world. So there are 2 offices here in the UK with the head office in London, office in Aberdeen. There is office in Norway, Kazakhstan, Qatar, Emirates, and US as well. So moving on to the topic of the discussion, to the CO2 storage in depleted gas field. So CO2 storage, it became quite a hot topic in the recent years, and it's quite widely discussed. It's quite an important part of decarbonization programs. So there is a lot of interest and attraction to CO2 storage. And today I'll show a little bit on our screening study for the CO2 storage in the depleted gas reservoir. It's a confidential project, therefore I cannot share a lot of details or a lot of numbers here. So you'll see that some of the axes are hidden, and I apologize for that. But I can give a little bit of background so we all understand what kind of reservoir we're dealing with and what are the average properties. So it's an offshore dry gas field. It is a sandstone, so the average thickness is quite variable from 260 to 780 foot. The permeability is quite low as well, and it's quite variable. So from PTA on the average, it's from 0.4 to 20 millidarcy. The average porosity is around 8%. There are 6 producers in the field. And the current model is a black oil simulation model done in Navigator, and it's 2.5 million active cells. So when we decided to look at CCS screening for this particular field, we split the project into 2 phases, and phase 1 was concentrating more on the injectivity of the wells, if the well can actually be used for CO2 injection, if they can, if they can inject, what are the pressure regimes that we would expect at the COP in the reservoir, what are the pressure regimes within the wellbore, and also evaluating the theoretical storage capacity. But theoretical storage capacity, it should really be treated as a maximum because there are a number of factors. It doesn't really account for the pressure constraints, for the injection strategy, what wells are injecting. And in this particular case, the injectivity is quite variable between different wells throughout the field. So it doesn't, the theoretical capacity, it doesn't account for heterogeneities as well. Hence, we decided to take it further to the second phase of the screening and take it to the full field simulation model and to see if we can do it with Navigator as well. So the key questions during the screening process to answer were if the subsurface environment is actually suitable for CO2 injection, if the storage site can be developed cost effectively, and what is the maturation potential and the commerciality of the project. I'm not going to talk about any of those, except I will concentrate a little bit on the capacity and on the injectivity. So the practical capacity evaluated using the simulation model in Navigator, and we looked at the geomechanics, so rock mechanics were introduced in the study. So we developed the workflow to look at the CO2 injection. And as I mentioned earlier, we have dry gas. So the initial model was, of course, the black oil model developed for gas production and, well, the gas history and the forecast. So in order to make it suitable for CO2 injection, we need to convert it to the compositional model. So we built an equation of state for the native gas and for injected CO2. So we needed to make sure that the 2 models, the black oil and the compositional model, they're consistent. And also we ran some sensitivities on the number of components, because we have injection, we have the production history, we have the production forecast, and also we have the injection history. So the running time is quite important here. Then we want to convert the black oil model into the compositional modeling, so building the new saturation modeling, implementing the developed equation of state. And we needed to make sure that there is consistency between the 2 models, that our volumes are consistent and that our pressures are consistent as well. So once we were happy with the compositional modeling, then we could build on the prediction cases. So we could convert the injector or the producers into injectors, into CO2 injectors, and build the injection scenarios looking at the different wells and run the sensitivities on the injection rates as well. So there is another aspect to CO2 which is geomechanics, because of course we want to inject CO2 and we want to store it for hundreds and thousands of years. So we want to make sure that the containment is not going to be compromised with the assumptions that we used. So we needed to understand what is the highest pressure that we can repressurize the reservoir to, and also what is the maximum dP that we can introduce safely in the reservoir. So the prediction runs with two negates for approximately 4 to 8 hours, depending, of course, how long or how many wells and what is the injection rate and for how long the cases were run. So to talk a little bit about the phase diagram of CO2 compressed and transported in a liquid or dense phase, and we want to maintain this dense phase all the way throughout the system, so from the wellhead to the reservoir. And we want to make sure that there is not much of the free water present nearly at all times, because of course it can increase your corrosion rates to, well, by quite a magnitude. So if you look at the phase diagram, we have pressure and temperature, and for the pure CO2, we don't have the two-phase region, but as Eduardo showed you earlier, with increase of impurities, we would have the widening of the two-phase region. So this is the critical point for the pure CO2. The critical point is 31 degrees Celsius and also around 74 bar. So from the at the highest pressure, at the high pressure, the CO2 is in a liquid phase. Everything below the critical pressure, it's in a gas phase, and then at the higher pressure and temperature, it's in a supercritical phase. So supercritical means that its density is similar to liquid and its viscosity is similar to gas. So it weighs like a liquid but flows like a gas. And if the importance why I stopped a little bit more on this phase diagram, because especially we need to understand what is our phase of CO2 all the way through the wellhead to the reservoir. So ideally we want to maintain the dense phase all the way through, because if we were to change the phases between the liquid and the gas, there could be a few issues introduced to the whole system. One of them, if we were to look at the density, once we approach at the density of CO2, especially at the lower temperature, once we approach the critical pressure and temperature, there would be quite a significant step change in the density, meaning that we may potentially have quite a bit of well control issues, but also that may introduce quite significant Joule-Thomson effect. So we may introduce some hydrate formation in the reservoir or in the wellbore. Hence, we do need to understand what is the pressure regime throughout the whole system. The CO2 is a buoyant fluid, so it's going to migrate to the top of the reservoir, and hence, again, to highlight the importance of the geomechanics, we need to make sure that the how strong is our cap rock, what is the maximum pressure we can introduce to the system as well. So for this particular field, the initial reservoir pressure is around 400 bar. The depleted reservoir pressure is somewhere from 75 to 132 bar, which is quite close, quite similar to the critical point, however, above the critical pressure. So giving us quite favorable conditions in that sense, but also that means that we have around 326 bar pressure that we can repressurize the reservoir to. The ambient reservoir temperature is around 227 Fahrenheit, and bottom hole tubing temperature during the injection is around 108 bar. So again, once at the end, at the COP of the reservoir, in this particular case, we are close to, but just slightly above the critical pressure. So in order to convert the black oil model into compositional model, of course, we needed to look at some assumptions and introduce some modifications to the modeling. So as a given, we have dry gas field, we have black oil simulation model that is history matched and forecasted. So we needed to look at the equation of state, make sure that it's consistent. We ran the sensitivities on the number of components, and we initialized the runs with the water saturation grid of the black hole models. So we had consistency in the in-place volumes, and we rebuilt the saturation tables in order to be suitable for CO2 injection and the compositional modeling as well. We needed to make sure that the history match is maintained, meaning that we have the same volumes at the same initial volume in place, and also the same volumes at the COP. So essentially that it's between our base case assumptions that we've done in the black hole model and positional model, that we have the same voidage space available, and that the pressure regime is maintained as well. So for this screening study, we did use 100% CO2, but as Eduardo already highlighted, it is indeed very important to introduce the impurities. So this is the screening project, and in the future, potentially we will introduce the impurities in it, because of course it's going to affect your plume development. Of course, it's going to affect your flow assurance as well. So once we were happy with the model, with the history match, and with the forecast, we could start building up the prediction for the CO2 injection scenarios. We needed to make sure that the start date is the same, so we are at the same pressure for all the cases consistently. We controlled the injection by the constant rate to maintain the plateau rate, assuming we have stable, steady supply of CO2 throughout the years. We have some pressure constraint that we did need to introduce, which is we have constraint from the facilities point of view, but also from the reservoir point of view. It is more relevant at the later stage of the simulation. So of course, at the initial level of injecting and depleted reservoir, we're at a quite low pressure, but as we start injecting, the pressure is going to be gradually building up. And then we need to make sure that we do look at the pressure constraint as well, that we understand from geomechanics what is the maximum dP we can introduce in the reservoir and what is the maximum pressure we can repressurize the reservoir to. So in order to investigate individual wells injectivity and field suitability to store CO2, also in order to look at the plume development, if there are any constraint to the flow, what is the effective storage capacity of the field. We convert the black oil into the compositional modeling, and also we needed to convert producers into injectors and then start building up on the injection scenario. So initially we started looking at the individual wells injecting on 1 megaton per year, and then we could start building up the scenarios on top of it, looking at the different wells combination and the different rates as well, going from 1 to 5 wells and from 1 to 5 megatons per year as well. There is quite a bit of heterogeneity in the reservoir, and it is quite important on which wells are injecting from. So injectivity is quite variable throughout the reservoir. So looking at the plume development for this particular scenario, it's a cross section. So these 3 plots here on the right, it's a cross section going between these 2 wells, and we have injection from the 3 wells here. We are looking here at the CO2 mole fraction. So pre-injection, of course, there is not much CO2. And then as we start injecting, and we can see the CO2 gradually propagating throughout the reservoir, but also we can see on the other side where there is no injection, we still can see CO2 propagating throughout the reservoir. So again, there is a heterogeneity in the field, and there are some faults in the field, but we could see that there is no significant plume restrictions again, in this particular case. If we look at the pressure map as well, so this is slightly different cross section. It is the same case, so but the cross section is going all the way across the field here, and when we pre-injection, we have quite a high level of depletion around the throughout the field because the wells were producing. But then once we start injecting, we can gradually see the pressure building up around the wells, around the injection wells. But also over the time, we can see the pressure building up all the way across the field, which is can be, well, it's double-edged sword as well, because on one side it's our capacity, it's our storativity, but on the other side as well, let's say if we have a low supply of CO2, but some of the wells have too high injectivity for this particular rate, then potentially we can start injecting with weaker wells, building up the pressure, and then introduce the other wells. And again, it comes hand in hand, tying together with the injection strategy that we need to look at. So to conclude, we looked at the pressure regimes within the reservoir, we looked at the pressure regime within the wellbore as well. Yes, at this particular stage, it is the pure CO2, and that can be taken further for the looking at the impurities, which is important because of course it's going to affect your two-phase region and the critical point as well. But as a screening study, that's what we used. And then we found out that the field is potentially suitable for CO2 injection. The reservoir pressure is quite favorable as well, as we are above the critical point, and it gives us an opportunity during normal operating conditions again. So it does give us an opportunity to avoid the phase changes, but also we were able to evaluate the effective or practical storage capacity of the field. We looked at the geomechanics, and the cap rock in this particular case is very strong, and we can repressurize the reservoir up to initial levels. As we would inject, we would of course introduce potentially some small fractures or reopen existing fractures, but it's by no means going to be with the DP that we consider, it's not going to compromise the seal, it's not going to affect the faults as well. So the reservoir modeling work showed that we have no significant restrictions to plume development. So even though there is heterogeneity, and even though there are some faults in the field, but we could see the CO2 is capable of propagating through the reservoir. So I think that is my last slide. Thank you very much. And yeah, I think I will pass to Max now. Let me stop sharing.
Thank you very much, Anzhela. That was really interesting. I've actually seen that presentation before, but it's much easier when you see it on the screen. So we've got quite a few questions. I think I'll start. I think Barney's going to join me by asking some of them, but Vincent originally asked just at the beginning there, what was the pressure at the start of injection? I think we saw that in one of the slides. It's around about 75 to 100
Yes,
bars.
it's 75 bars and above, yeah.
Yeah, and they said if very low pressure, was there constraints in the Joule-Thomson cooling effect? But I think we addressed that.
Yes.
We say we just about avoid that.
We just about, yes, indeed. And there are, again, so there are different possibilities, different options to look at it. So depending where is your economic COP, so can you stop production earlier, which of course, probably from gas production perspective, it's not ideal, but yeah, you need to look what is your pressure regime. And again, it's one case, one scenario. So you would have some uncertainty, of course, in the reservoir pressure, especially at the end of COP, given a number of years ahead.
Barney, before you jump in, I'm just going to address Adrian's question. It says, when using subsea wells, not platform-based, downhole chokes are required in the injectors. How does this affect the modelling, and how demonstrated are downhole chokes for CCUS today? Now, I think you'd be able to comment on how does it affect modelling, but I'm not sure about how demonstrated chokes are. What do you think, Anzhela? I think in terms of at least the reservoir injectivity point of view, we need to maintain a set injection rate, and therefore the chokes will be very important. But when you're having a shot in, you go ahead, Anzhela, sorry. See the question?
Yes. You're on mute there, Anzhela.
Yeah, sorry, I was looking at the questions. I was trying to find it. Sorry. Yeah, when using subsea well.
Maybe you want to jump in as well, Eduardo.
Yeah, I think I really need to think about that question, to be fair, because yeah, we do need the downhole chokes, and
maybe we'll move on to the next question then.
I think, yeah, sorry, yeah.
So Eduardo, this one's from Christoph Kirsten. He says, thanks for your talk. When considering impurities, I expect that, for example, 50 ppm-V of oxygen impact the material selection, but not the phase envelope. From a practical point of view, I would limit the CO2 composition to 3 to 4 species like CO2, hydrogen, nitrogen, and possibly methane. What are your ideas / recommendations about this? So quite an open question.
Yeah, thanks, Christoph. I think this, and probably I should have mentioned it, no? But also it depends on whether you want to use that composition for, for modeling purposes. Of course, if you want to do flash runs, so pilot modeling, you are correct. You don't need to have the 40 components, and you are quite correct. Maybe those components that you mentioned, and possibly methane, argon, are the ones that are going to be more impact your physical properties. However, if you're going to model a dew point, for example, then you need to include stuff like glycols or amines, because that's, and also other impurities, because that's going to really shift your dew point to different pressures. No? So yes, I think for when you said to limit the CO2 composition, I think yes, but it depends on where you want to use that composition. And I'm possibly you are referring to the modeling point of view, but.
All right, thank you. Bertrand asked, what are the components of the equation of state? Am I right in saying it's 100% CO2?
So yeah, but then we have indigenous gases also. We have the nitrogen, we have the methane, we have the ethanes, the CO2, of course, the yeah. And from equation of state point of view, we did need to make sure that we have consistency between the two, with the indigenous gas in the field as well.
And Paul asked, how likely might the injection pressure exceed the formation fracture pressure in this case? So I think you addressed that by saying that, I mean, at least from my experience.
Yes, and at the fracture pressure, so we have the existing wells, and that's one of the benefits of the existing fields, that you have information, that you have the wells drilled, you have production history. And so we looked at the fracturing pressure, and of course, as your reservoir depletes, your fracture pressure is going to be reduced as well. So we do exceed, in this particular case, we do exceed the fracture pressure by quite a margin, but it's not, from the geomechanics point of view, it's not going to exceed our limitations, and it's not going to compromise our seal as well, so our cap rock.
So Neil asked a question about the fracture, the heterogeneity of the field, but I think you addressed that in the presentation, so I'll skip past that. Abdullah Allah, sorry if I've mispronounced that. Yeah, I'm not sure. Hi, Anzhela. How did you rebuild the saturation tables, both relative permeability and capillary pressure?
Yes, that's correct. Yeah.
That's correct. Yeah. So Steve, your minimum depleted pressure exceeds 1,000 psi. How representative that is going to be a commercially depleted reservoir? I think you said there that from a pressure management point of view, you would want to maximize the recovery of gas.
So yes, so there is. Well, depending on the field, right? What is your economic COP? Because in some cases you cannot go to as low as possible because it may not be economic. So in this particular case, our at the COP, the reservoir pressure is above 1,000 psi, well, above 1,060 psi. However, indeed, if you look, it depends on the reservoir that you're looking at. So at some high permeability reservoir, you would have the recovery factor of over 90% in some cases. And then of course, your reservoir pressure is going to be way lower than that. And then hence the screening study come into play. So you need to look at and screen, yeah, if the reservoir is suitable. So there were two sides to it as well, because there the higher the recovery factor, it's your voidage space as well. So your remaining gas in place, your residual gas, the lower it is the better, because you have much voidage space, but then that means the pressure is quite low. And then you start having all the issues with the phase changes and the Joule-Thomson effect. It's going to be near wellbore, or is it going to, because as you would inject, it can happen even further away from the reservoir. You're going to pluck up your pores as well. So that's something that needs to be looked at and addressed in the study. So again, that depends on the individual case.
Thank you. There are two questions here that I'm just going to address from Mohammed and Adrian, talking about solubility and trapping mechanisms. So from what I know about the project is that we did a study, looked at the residual stratigraphic and solubility trapping. So had turned on CO2 sol, had a look at what effect that had.
Yes, and T-Navigator is able, same as Eclipse, same as T-Navigator, is very capable of capturing it with CO2 solubility, and you can capture it with the equation of state as well as the, yeah.
And in terms of in terms of the mineral trapping, so in terms of sandstones, at least quartz is very inert in the presence of CO2, which is the predominant mineral there. I did my master's thesis on mineral trapping, and I can tell you, yeah, you probably wouldn't expect very much for thousands of years, but perhaps with more reactive reservoirs where it's a little bit more heterogeneous in terms of the lithology, you might have to investigate that. And a way to do that, you would use TUF or maybe freak-C, looking at more subsurface geochemistry and the different software packages that can capture that. Okay, let me see if I can find one for Eduardo. We've got quite a lot of questions in the chat now. Here's one from Matteo. According to your experience, Eduardo, is it the solid phase formation risk CO2? Is that a risk, solid phase formation, when the presence of impurities?
No. No, I think one of the issues also is that, as you may know or know, to predict the equilibrium of solids or vapor liquid solid equilibrium is quite complicated. So using a traditional equation of state is not that simple. You need to do something else to modify the equation of states. And I know that the property packages, they have some sort of a solid formation prediction, but that's okay if you have pure CO2. But once you have impurities, again, you have the same issue, no? Because other impurities also may freeze, and that actually those are not well predicted with the current models.
Right, thank you very much. Unfortunately, we're running out of time here. I think we could probably squeeze in one more. I'm just going to scroll up and try and find one. Mohammed Arif said, "Hi, Anzhela. Thank you for a very inspiring talk. I appreciate you addressing my questions. Can you calculate the theoretical CO2 storage during the stage of screening? And what are the parameters / information you need to evaluate it?" This will probably be our last question.
Yes, so if I elaborate a little bit more on the theoretical storage capacity, essentially, well, that's existing field, right? So we know the production history. Well, of course, this is the prediction models, and but we have an estimate what is the voidage space essentially available at the end of the field life. So then you can look, and we know the difference between the fluid properties or indigenous gas and what is your formation volume factor of the CO2 as well. So we can essentially, we know the densities, we can recalculate. Yeah, it's just looking at the volumes, what was produced and how much voidage space we have available, and recalculate it back to CO2. Do you model the trapping?
Lots of questions.
Yes, I think we answered that as well. So solubility, yes, even though in this particular case, excuse me, we don't have much of the water, so we don't see much of the aquifer support, and we don't expect a significant amount of water at the end of field life. But we of course have some connate water, so we do have solubility and the structural trapping. Yeah, the mineral Max already covered that. Yeah.
All right. I think, Barney, we've run out of time. I mean, I'll maybe do one more question. I'm just seeing if there's anything here we haven't really covered. How accurate? I mean, here's from Chris's iPhone. How accurate was and predictive was the original black oil model for the original production project? I think you might be able to answer that very well, Anzhela.
Well, it's a base case assumption, as you all know. All models are quite often wrong, so, but it's the best assumption. So it is history matched and forecasted models. So, but then you can take it to any project. It's a model, right? You can't open the ground and say, oh well, that's what it is. So it's of course there are some assumptions in it.
And I have one final question just inside, since people are still hanging around. In terms of maturing a project beyond the point that we already have, what do you think are the next steps to get it over the line from, okay, we've had a look at the practical storage capacity, but I think Eduardo and Anzhela might be able to talk about this, about how do we actually get more accurate modeling with introducing impurities, et cetera, and also having a look at those trapping mechanisms. What do you think? Anzhela, do you understand my question?
Yes, you can. Well, as Eduardo already highlighted, the impurities are quite important, and some other cases we did look at it, and they do have quite significant impact, not only on your flow assurance, on your well, on your completion selection, on your facilities selection, on your plume development. So that's one of the things to introduce. Yeah, to introduce impurities, then build upon the different scenarios as well. Because if it's existing field, then you need to look down the line. So it's production history, production forecast, and then you probably would have a bit of a range at the end of COP, and then there are injection stretches as well. So that's another thing to increase the accuracy. And
yeah, and I think that the important thing is that if you consider a fixed composition through the field, I think that might be also incorrect. Because, as I said, that you're going to have different sources with different impurities. So that composition is going to be changed through life of field. I'm sure that's going to affect, eventually what compression, what sort of facilities you need, but also the storage itself. So you're going to be storing less or more that you were predicting if you do a screening exercise, just considering pure CO2.
yeah, it's the densities as well. So it's going to affect the pressures. What's the injection pressure? Yes.
All right, I think I'm gonna wind up now. Barney, thanks for helping me organise this today. I want to thank the sponsors OPC and ERC Evolution. I want to have a big thank you to Eduardo and Anzhela for presenting today, and a thank you for everyone for attending and all of your questions. We really appreciate it. I've put in the chat if you want to get in touch with either Eduardo or Anzhela for any additional questions, please feel free to. And we can share the presentations and the recording afterwards on LinkedIn. But yeah, overall, big thank you for everyone and for attending, and thank you to both of you.
And thank you, Max, for organising it. Great job. And thanks to the audience for attending. Hope you enjoyed it.
Thank you very much now. Bye-bye.
Thank you very much. Bye.
Thank you. Bye.